So we're going to start taking a look at how to take the Laplace transform of any sort of function that might have the unit step function incorporated into it. So this first one that we have is Laplace transform of e to the 2 minus t unit step function of t minus 2. The goal is to be able to make the interior and the interior functions look the same. All right, so anything that's a composite function, we need to make them both t minus 2, and we can't really alter the t minus 2 that's inside the unit step function. So here's what we're going to do. We're going to rewrite this as Laplace transform of e, and we're going to factor out a -1, e to the t minus 2, not 2 minus t any longer. So we're just doing some algebra to make it look the same. And then unit step function of t minus 2. All right, now what we're going to do is we're going to employ the second translation theorem. Okay, so this is our second translation theorem. And that means that this is going to turn into, in this case, we have a is equal to 2. And you might recall that if we have a t minus 2 and a t minus 2, this is just going to turn into an e to the minus as of f, or the Laplace of f at t. All right, so that's how our Laplace transform worked for that. And so let me get rid of this and try to write that a little bit more legible. So it's going to be e to the minus as and then the Laplace of f at t in this case. And so in this case, what we could do is we could use the second translation theorem, and now this is going to become the Laplace of e to the minus 1t, and this part and the unit step function, all right, are just going to become e to the minus 2s. Right? And now we could just take this, and you might remember that anything with an e, now that's actually going to become the first translation theorem. All right, so this is going to become the Laplace of 1 as s approaches s plus 1. Right? E to the minus 2s. And so finally, this is actually going to turn into e to the minus 2s times 1 over s plus 1. All right, because remember the Laplace of 1 is really 1 over s, but it's approaching s plus 1. Right, so this one is just our first translation theorem. All right, so this is an example where we used both of the translation theorems to get to our solution. Another example, and this one's a little bit scarier. We have this Laplace of 3t plus 1 unit of t minus 3. And so again, the goal is to try to make these two interior functions look the same so we can use the second translation theorem. And again, we can't change the unit step function's interior. So here's a trick that we can do. What I'm going to do is I'm going to factor a 3 from this first part because I needed to get to t minus 3. And so I'm going to rewrite this as 3 Laplaces of t plus 1/3 unit step function of t minus 3. All right. And we had to do that because there's no other way to make 3t look like this t. Now, the trick is at this point, well, how do I get this guy to look like a 3? All right, so we're going to do that trick that we saw earlier with Laplace transforms. All right, so here's a sneaky trick, is we're going to rewrite this as t plus 1/3, and we're going to do that trick where we are going to subtract and add some number. And in this case, it's going to be 10/3. All right, and I'll illustrate why we do that in a moment. Unit step function of t minus 3. All right, now bear with me on this one. If we combine these, well, that just gives us -9/3 or -3. So we just wanted to subtract something to be able to get us to the -3. But we still have this animal right here, this positive 10/3. But that's not a big deal. So what we're going to do is let's rewrite it. And we're going to have 3 Laplaces of t minus 3 plus 10/3 times the unit step function of t minus 3. All right. Now, this is actually really cool because now what we can do is we can take the t minus 3, distribute it to the unit step function, and then the 10/3 and distribute it to the unit step function, and we can get two separate Laplace transforms out of that. So this is what we're going to get. 3 Laplace of quantity t minus 3, unit t minus 3. All right, so that's our first distribution. So that's this part. And then we still have the 10/3. And so that's going to be plus 3 Laplaces of 10/3 times the unit step function of t minus 3. And now what we can do is we can use that second translation theorem. All right, so our second translation theorem says that, okay, well now our second translation theorem, that's not 2 pi. Let me write that a little bit better. That's second translation theorem. It's going to say that instead of t minus 3, that's going to become e to the minus 3s. And instead of t minus 3, that's going to become e to the minus 3s. Right? And so here's what we get. By employing our second translation theorem, we get 3 Laplaces. Instead of t minus 3, that's just going to become a t. And this guy right here, as well as the t minus 3, is going to become our e to the minus 3s. On our other Laplace, this is going to become 3 Laplace of 10/3 and e to the minus 3s. Now we can finish this off. All right. Notice that there's no e inside of here, so we don't need the first translation theorem. And so what we can do is, in fact, if we really wanted to, we could just factor out this 10/3, and 10/3 is going to come out, and we can multiply it by 3. So the 10/3 times the 3 is just going to turn into a 10, and this will just become a 1. So notice I just multiplied that. There's that rule with the constants. And so now this is going to become 3 over s squared. Okay, so remember that rule is that this is just going to be 1 over s squared. We still have the e to the minus 3s, and then we're going to have 10 times 1 over s. So remember, Laplace of 1 is 1 over s, and then we still have that e to the minus 3s, right? If we really wanted to, we could factor out a 1 over s e to the minus 3s, and we get our answer for that. Right. One last example that we can do. Let me go ahead and move that back, see if that'll work. It didn't look like it worked. So, all right. So one last example that we can do, all the way down here, is we can find the Laplace of t, e to the t minus 4, and then times the unit step function of t minus 5. All right, so this is actually a pretty ugly one. So we're going to have to do a number of things. So notice that we have a t here, a t minus 4, and we have to make them both look like t minus 5. All right, so now we could use the easy trick on the first one because we've seen that. So we're going to write this as Laplace of quantity t minus 5 plus 5. All right, so that's the first t. Now what about this e? We need that to be e to the t minus 5. So here what we're going to do. We're going to multiply by e to the negative 1 times e to the 1. All right, and we know that that's just e over e, right, which is just 1 anyway. So that's completely legal. So we didn't do anything illegal there. And I'll show you what we can do with that in a moment. And that's going to be still times e to the t minus 4. And then we have that unit t minus 5. All right, that's a minus 5, by the way. All right, so now let's just pick on this e for a moment, all these e's. All right, and let's just ignore the t minus 5 there. So if we do that, we still have our Laplace. We have t minus 5 plus 5, so I'm not operating on that. I'm going to combine this and this. And what we could do is we could just add the exponents together. So that's going to be e to the t minus 5. And so we're good with that one now. What about this e to the first? It's a constant. Let's pull it on the outside. Right? And now we have unit of t minus 5. And now the problem's looking familiar, much like the previous problem that we did. Now we can distribute. We can take the t minus 5, distribute it, and then the 5 to distribute it. And we can go ahead and get 2 Laplace transforms out of this. Okay, so it's going to look a little ugly, but don't worry too much about it. So we're going to get e Laplace of t minus 5, e to the t minus 5, and then unit step function of t minus 5. And that's 1 Laplace. Then we still have that other 5. All right, so we're going to have plus e Laplace of 5 e to the t minus 5. And I'm going to squeeze in the unit step function. All right. So now how does that work at this point? Okay, well, what we're going to do is we're going to go ahead and rewrite this now using the second translation theorem on both of these. So second translation theorem, and I did it again where I made it like pi. So our second translation theorem and our second translation theorem, all right? And if we do that, all the t minus 5s are just going to go away, and they're going to become t's, and the unit step function is going to completely go away. So we're going to get e Laplace of t, e to the t, and right here we know that a is equal to 5 in our second translation theorem, so that's going to be equal to e to the minus 5s. Right, so that's nice. And then even better, this one's going to turn into something really easy. The 5 can come on the outside, so we're going to get plus 5e, and then we're going to have e to the t, and we have our e to the negative 5s. All right, so again, the unit step function and all the t minus 5s are just turning into this e to the minus 5s. All right, that's what it does. And now we can go ahead. On this one, we have a first translation theorem. All right, so that's going to be as s approaches s minus 1. So let's just set that one up. So we're going to have e Laplace of t as s approaches s minus 1. Okay, and that's old stuff. That's our first translation theorem. We still have that e to the minus 5s, and then we have plus 5e. And we can use the first translation theorem on this one again. So that's going to be of 1 as s approaches s minus 1, and we still have the e to the minus 5s. All right, so now I'm going to write the answer in a few ways, all right, just because if you were to check this by utilizing Wolfram Alpha, you might get something completely different. So one possible answer is going to be e times e to the minus 5s. And when we take the Laplace transform of t, that's 1 over s squared, but we have to plug in s minus 1 from the first translation theorem. So that's going to be times 1 over s minus 1 squared, and then plus 5e. We know the Laplace of 1 is 1 over s, but we have this s approaches s minus 1. So it's going to be actually times 1 over s minus 1. And then we still have that e to the minus 5s. All right, now that's a perfectly viable answer. No big deal with that one. If you want to, you can combine the e's. Right? And so another way to write this answer, not any more right or wrong, just different, is we could write this as, because these are e to the first power, and so our algebra says that we can write this as e to the 1 minus 5s over s minus 1 squared, and then plus 5e to the 1 minus 5s over s minus 1. All right. If you wanted to get a common denominator, you could do even further and do that. All right. but this might be a pretty good answer as to what to expect with the Laplace transforms. Okay, so a little bit sticky being able to do these, okay, but hopefully you can see how to use the second translation theorem in tandem when necessary with the first translation theorem and all the Laplace transforms that we've seen. Now in the next video, we're going to go backwards and we're going to take a look at the inverse Laplace transforms for unit step functions.